So today we will start a new section and it's called logic gates and Boolean algebra. So in this we will see logic functions with ones and zeros, and we will build some digital circuits or logic circuits. We will look at truth tables, Boolean algebra and its properties. Then we will see how to minimize functions and how to transform our Boolean functions. So if we are given a task, for example, in this case we will have some kind of inputs here and we will have some outputs, and then we need to design a logic circuit or digital circuit to implement this. But there are many possible implementation. So what we will try to do, we will try to design the best circuit, right? Best circuit in terms of it could be size, the minimum size or minimum power, or it could be higher speed, okay? The highest speed that we can get. So what might be a simple example? For example, we can try to design a tool booth controller. So for example, in a parking lot, we might have a gate. We will open this gate or close the gate if we have some inputs. Let's say I will require 1 Turkish liras as an input, and if the car is present, then I will have 1 output. I will say, based on these input, either I open or close the gate in the parking lot, right? So I can call this is my I1 input and this is my I2 input, which detects if the car is present at the gate. So to implement these logic circuits, we need these input variables, or we will call it binary variables. So we can name it A, B, X, Y, Z, right? And these could be 0, 1, false, true, high, low, on, off. So these variables represent either false, true, high, low, on, off, right? Or we could have more meaningful variables such as clock, reset, add signal, or start signal. So using these binary variables, we need some logical operators, right? So we will process these inputs using these logical operators. So these logical operators, they operate on binary variables and binary values. So what are those? For example, AND operator, right? So we can represent it with a dot. So I can say Y is equal to A and B. So another logical operator is the OR operator, and I will represent this OR operator with a plus sign. So remember, this is an OR operator. It's not doing an addition. This is just a logical OR operator. Another logical operator is this NOT operator. So I can represent it with a tilde or a bar sign such that I can write C is equal to A not, or you can just say C is equal to not A as well. So similar to logical operators, we can represent these operations by the logical gates. So we might have this NOT gate. So this is our NOT gate symbol. So if I have X input and this is Y output, so the Boolean equation that I will have is Y is equal to X not. So this is the Boolean equation or Boolean function. Then I will have also a truth table for this gate or operation. So I write first the input, then the output Y. If X is 0, my output is 1. If my input is 1, then my output will be 0. So this is my truth table for this NOT gate. So similarly, we will have this AND gate. So this is a 2 input AND gate. Let's say my X and Y is my inputs and Z is my output. The Boolean equation is Z is equal to X and Y, and the truth table. So I need to first write my inputs X and Y, and I will write my output here. So now I need to list all possible input combinations. So X could be 0, Y is 0. X could be 0, Y is 1. X is 1, Y is 0. X is 1 and Y is 1. So this is the 4 possible inputs, and these 4 possible inputs. So what is the output? So this is 0, 0, 0 and 1. So in the AND operation, if any of the inputs is 0, the output is 0. So output is 1 if and only if all the inputs are 1. And the last logical gate is the OR gate. Again, x and y is our inputs. So this is our OR gate symbol. Let's say z is my output. Then the Boolean equation is z is equal to x or y. And let's write the truth table for the OR gate. Again, I need to write all possible input combinations, and then my output z is 0 in this case and 1 in the other cases. So for the OR gate, the output is 0 if and only if all the inputs are 0. The output is 1 if any of the inputs are 1. So let's see a basic application of an OR gate. Let's say I will design a simple intrusion detection system. So in this system, in my house, when any window or door is open, then I will activate my alarm. So let's say I have a window here, 2 windows and 1 door in my home, and let's say I have a sensor here. Let's say this is S1, this is S2, and this is S3. So this sensor detects if the window or door is open. If any of them is open, I need to give a 1 to the output. So for this, I need to use an OR operation. So if any of this is open, then let's say my output is A, and this is, let's say, alarm circuit. So I will activate my alarm if any of my door or windows are open. So I can represent this in this Boolean equation. So let's make an example for the AND gate. Let's say I will design a simple seatbelt alarm. Okay. So in this case, if the ignition is on and seat belt is off, and after some time, let's say, and some specific time, I will make my seat belt alarm sound. Okay. So let's say I have this ignition sensor and it needs to be on. And I also, if this ignition is on, I also need to have some kind of timer that will count for me for some specific time. Let's say for 2 seconds. If this is true, if the timer is, let's say this will give me a 2 second. If the 2 second is true, and then if the seat belt is off, right? Let's say this is the seat belt sensor S. If this seat belt is not locked, then I will make sure my alarm circuit will warn me. So in this case, A is equal to, let's say this is ignition is I. Let's say this is my T, I and T and S not, right? So this seat belt sensor is off if seat belt is not fastened. Okay, so these were some very simple examples for this AND OR gates and NOT gates. Now let's look at the Boolean algebra. So we use it to specify functions as well as to transform or minimize our functions. So we will also use it to design or analyze, for designing or analyzing our digital systems. So basically Boolean algebra tells us how we can operate on our binary variables. So these are some properties. So the first property is, if I have a variable x and if I OR it with 0, the result is the same, right? So if I have a variable x and if I AND it with 1, and my output will be still x. So if I have a variable x and if I OR it with 1, the result is 1. Another property, if I have variable x and if I AND it with 0, the result is 0. If I have a variable x and if I OR it with itself, the result would be x. So if I have a variable x and if I AND it with x, the result is x. So if I have a variable x and if I OR it with its not, then the result is 1. If I have a variable x and if I AND it with x not, the result is always 0. So if I have a variable x and if I take its not twice, I will again get my original variable x. Okay. Another property, if I OR my variable x with y, it is same as I OR variable y with x. So if I have x and y, this will be equal to y and x. So if I have x or y or z, this is equal to x or y or z. So if I have x and y and z, this is equal to x and y and z. So if I have x and y or z, so this is equal to x and y or x and z. So similarly, if I have x or y and z, this is equal to x or y and x or z, right? So I am distributing this x on these two y and z variables. So it is also possible to do this in Boolean algebra. So the other two properties called De Morgan rule. So in this case, if I have x or y and not of this operation, this is equal to x naught and y naught. Similarly, if I have x and y naught, this is equal to x naught or y naught. Right? So you are taking this not operation and applying to it to each variable, and then this operator is becoming, if it is an AND operator, it is becoming OR operator. Similar here, right? So this OR operator becomes an AND operator, and we take this not and apply it to each variable. So let's try to prove this De Morgan rule, right? So how do I prove this? One way of proving this, I can use the truth table approach. Let's say I have these x and y as my inputs. So all the possible cases are here. So if I have x or y, so this will have 0, 1, 1, 1. So if I have x or y naught, then I need to take the inverse of x or y, right? So this will be 1 and the others will be 0, right? So basically what I did, I found this operator. So now let's find x naught and y naught. Then after that I can find x naught and y naught and. So x naught here is 1, 1, 0, 0. Y naught here 1, 0, 1, 0. So if I take AND these two, right, with an AND operator, I will have 1 here and 0, 0, 0 here. So now if you look at these two columns, you see they are equal. So I proved this De Morgan rule is correct. Similarly, you can also use the same truth table approach to prove this property, right? So another property is, given a variable x or x and y, this is equal to x. So how do I prove this? So if I take this x out, so this will be x and 1 or y. So 1 or y, so this is 1. So x and 1, it will give me x, right? So this was another property of Boolean algebra. Yet another one, let's say x and x or y. So this is equal to x. So let's prove this. So this will be x and x or x and y, right? So x and x is x. So x or x and y. So we already seen this here, right? So this is equal to x. So this was another property. So now let's use this Boolean algebra properties and then do some minimizations. Okay, so given this function, Boolean function, let's try to minimize it using these Boolean properties. So what I can do, so I can distribute this plus in these two variables. So right, I can write a or a naught and a or b. So what is this? So this is always 1. So the result is A or B. So this is a simpler function, right? Compared to this, we have minimized our function. So if I draw the circuit for this, I have A, and then, so this is my A naught. Let's say this is B. Make it smaller. So this is my original circuit. So this is A or A naught B. But if I minimize it, this is all I got, right? So this is much simpler, right? Instead of 3 gates, I only use 1 OR gate. Okay, let's do another example. So I am given this function A or B and A or C. So if I try to minimize this, then I will have A and A or A and C or B and A or B and C. So this is A, and if you look at this, this will be also A, right? A plus A and C. This will give you A. And then I will have A or B and A. So this is again A. So the result is A or B and C. So this is the simplest that I could get. So the original circuit, it was like this. So this is B, let's say this is A, this is C. So this was my original circuit, but I minimized it to this. So instead of 3 gates, I implemented the same thing with 2 gates. And let's do one more example. So I am given this function A or B naught and C and D naught and the naught of everything. So let's try to minimize it. So now I will have A or B naught, and let's take care of this NOT operator. So I will be putting a NOT here and converting this to a OR operator, and I will have CD NOT, and then I need to put another NOT here. So now I will have these 2 knots will cancel each other, right? I will have A or B or CD. So this is the final result. A final example with this Boolean operations. So in this case, I have A or B not and C, another not here, and then or CD not or B, another not, and then I will take not of everything. So let's try to minimize this. So let's take care of the top not operation. So I will have A or B and C. So this I will have these 2 and they will cancel each other. This OR operation will become an AND operation here, and then I will have CD not or B, because this one and this one after distribution they will cancel each other. Now, so here we still have a NOT operator here, don't forget it. Now let's take care of this. I will have A naught and B naught and C and CD naught or B. So now if I multiply this or AND this with these, so I will have A naught, B naught, C and CD naught, or A naught, B naught, C and B. So as you see, I have B naught and B here. So this goes to 0, and here I can open this, so I can write A naught and B naught C and C naught D naught. Then I can write A naught B naught C C naught, or A naught B naught C D naught. So since I have C and C naught here, this will go to 0, and the result is A naught B naught C and D naught.